Continuing with lesson 1-2 on page 17. Example 2. Write rational numbers in decimal form, repeating decimals. A class votes on whether to change their school mascot. How can you express the number of students in favor of a new mascot in decimal form? So let's read this bit right here. In a class of 18 students, 5 voted to change the mascot. So the way we're going to represent that information as a fraction is we're going to put the part on top of the whole. So the whole class is 18 students. So that goes on the bottom. That's my denominator. And the number of students that voted to change the mascot is 5. So 5 goes on top. So we have the fraction 5/18. Now looking at that, they're not both even numbers, so I can't reduce by dividing by 2. And I can't use my 3's trick. 5 is not divisible by 3, even though 18 is. In fact, I know that 5 is a prime number, so the only way for me to make 5 through multiplication is 1 times 5. So I actually can't reduce this at all because of that reason right there. So let's go ahead and turn that into a decimal using long division. So the way we're going to do that is we're going to set up our division right here. Our numerator goes inside and our denominator outside. We're going to ask ourselves, can 18 go into 5? Well, that answer is no. I'm going to put a decimal and a 0. Now, can 18 go into 50? Yes, 18 can go into 50. I know that 18 times 2 is 36, so let's start there. So when I subtract, I'm going to have to borrow. So this is going to become a 4, and this is going to become a 10. 10 minus 6 is 4. 4 minus 3 is 1, so I have 14. Now I'm going to add a 0 and bring that down. Can 18 go into 140? Well, yes, it can. I know that 18 times 10 is 180, so that's 40 too big. So let's try something like 7 and see where that leaves us. 7 times 8 is going to be 56. 7 times 1 is 7, plus 5 is 12. So 126 is perfect. So I'm going to subtract that. And when I do, I'm going to have to borrow. So this 4, I'm going to make a 3, and this is a 10. 10 minus 6, again, is 4. 3 minus 2 is 1. Notice I'm right back to 14. So even when I add a 0 and bring that down, how many times does 18 go into 140? Well, 7 times. 7 times 18 is going to be 126. We just did that. When I subtract, I'm going to get 14 again. So what I know is that 7 is just going to continue to repeat. So the decimal form of 5/18 is 0.277 or 0.27, and notice there's a line on top of it. That line on top of it, a line over one or more digits, indicates that those digits repeat. So because that 7 repeats, we put a line on top of that 7. Okay? Now, when we see this right here, that means that the decimal does not terminate. It does not end. It keeps on going. So I could write 15 sevens, and I'd still need that 3 dots to show that that decimal is going to continue going. So the reason we like this bar over the top of the digit that repeats is that it allows us to shorthand that decimal. Okay, so it's our turn to try it. What is a decimal form of 100 over 3, 100 over 5, and 100 over 6? Determine whether each decimal repeats or terminates. Okay, so if you remember our extra notes, I talked about looking at the denominators. If it's a multiple of 3, that means it's probably in all likelihood going to repeat. So I'm expecting those two to repeat. Now, our third one, the one in the middle, 100 over 5, I'm not going to expect that one to repeat. But we're just going to prove this with some long division. So I'm going to call this one A, this one's B, and this one will be C. Okay, so let's start with A, 100 over 3. So I'm going to write that for long division. So 3 is my outside number. It goes, it's my bottom number. It goes on the outside, and 100 goes on the inside. Now 3 doesn't go into 1, but it goes into 10 3 times. 3 times 3 is 9. I subtract and I get a 1. And I bring down that 0. 3 goes into 10 3 times. 3 times 3 is 9. I subtract that. I get a 1. And I'm going to add a decimal and a 0 and bring that down. 3 goes into 10 3 times. 3 times 3 is 9. Y'all see where this is going, right? Even if I add another 0 and bring it down, it's going to be the same thing. So I know that 100 over 3 is equivalent to 33.3 repeating. Okay, so that one is a repeating decimal, and that's exactly what I predicted because of that 3 in the denominator. So let's look at B. So B is 100 over 5. So let's set that up for long division. 5 goes into 10 2 times. 5 times 2 is 10. I get 0, and I bring the 0 down. 5 goes into 0 0 times. 5 times 0 is 0, and so on. So this one, because I have a 0 right here for my remainder, I know that this one terminates, it ends. So 100 over 5 is equivalent to 20. So this one terminates, it ends. It does not keep going. Okay, let's look at C. So here I have 100 over 6. So 6 goes into 100. 6 goes into 10 one time, which is 6. I get 4. And I bring down that 0. 6 times 6 is 36. I get 4. So I'm going to bring down a 0. 6 times 6 is 36. And y'all see where this is going, right? That 6 is going to keep repeating. So 100 over 6 is equivalent to 16.6 repeating. And we had suspected that it would be a repeating decimal because of that 6 in the denominator. It's a multiple of 3. Okay, let's look at example 3. Recognize rational numbers in decimal form. Explain whether each of the following is a rational number. So A, we've got negative 6.382. This decimal terminates. It comes to an end, so it's a rational number. Because it comes to an end, it is a rational number. B, 1.539981, 81 repeating. The digits 8 and 1 repeat infinitely. So this is a rational number. Okay? But let's look at this one right here. 0.43524982 ... What does this ... indicate? Well, hopefully you remember that it indicates that that decimal keeps on going. It doesn't end. So this decimal does not terminate, and the digits do not repeat. So this is not a rational number. Now it's our turn to try it. Is negative 0.3 repeating a rational number? Well, let's start by answering that first question. So we're focused on just this one right here. Is that a rational number? Well, it repeats. That line, remember, tells me that that digit repeats. So I would say yes, it's a rational number. Because it repeats. It repeats infinitely. It's going to keep going on forever and ever and ever. Okay, let's answer the second question. Is this number right here a rational number? Okay, well, here's what we know about that number. I'm going to expand it a little bit. Okay, I've got 3.14, 144, 1444, 14444. Okay, it looks like it repeats, right? But when I look carefully, I've got 1, 4, 144. Notice I have one more 4 added. 1444. Again, now I have 3 4s. 14444. 4 4s. So I've got 1, 2, 3, 4. So the number of 4s increases behind the 1. So even though this looks like it repeats, it does not repeat. Okay? So is this a rational number? Well, it's not a rational number because it does not repeat. And these 3 dots right here tell me it does not terminate or end. So, to answer the question, no, this is not a rational number because it does not repeat or terminate. It does not come to an end and none of the digits repeat. That's the end of page 17. See you on page 18.